Good morning, everybody, and it's a pleasure for me to introduce you Joanna Hart. Joanna is visiting us. Joanna has taken her master's degree in astronomy at University of Groningen. Then she moved in Munich. She took her PhD at HISO inside the AMPRS program. And then Joanna, she got a HISO fellow, postdoc HISO fellow in Chile, and she was a Muse fellow. And the actual position, Joanna now is a Finca fellow in Turku, in Finland. And Joanna is visiting us because we are working on the ultra-diffuse galaxies topic here in Naples, but today Joanna will talk about discrete tracers to map the intracluster light. So, give you the floor.
Thanks a lot for the introduction, Enrica. I've had a really great 10 days here. I've been really enjoying the lovely weather that Naples has put on compared to what we already have in Finland. So yeah, I'm going to talk about a multi-tracer view on the assembly of galaxy halos and also the surrounding intragroup light and nearby groups and clusters. I don't think I really need to outline the two-phase formation scenario of early type galaxies too much for this kind of audience, but I'm mostly going to focus on the second phase of the scenario where the cores of early type galaxies grow dramatically in size through mergers and accretion. And these accretion events leave behind telltale signatures. What you see here is a simulation from Bullock and Johnston, where you can see progenitors streams color-coded by their infall time. So you can see that the lightest colors, you still see the things that fell in most recently. But also what's very nice is that if you go far away from the centers of galaxies, that dynamical timescales are really long. So these structures live for a long time. So if you look in the halos of galaxies, we can really go back in time and understand the conditions of formation and of assembly over a long time frame, even though we just see, of course, one snapshot per galaxy, and it's not like in a simulation where we can integrate back and front. So in principle, this is the two-phase formation scenario, but there is an additional step that happens when galaxies interact, especially in dynamically rich environments such as groups and clusters, and this is building up the intragroup light. Again, if we look at simulated galaxies, for example, here, I think it's from the EGO simulation, we can tag every galaxy, every star particle, and basically ask it, hey, which subhalo do you belong to? And then we get something like this. You can clearly see we have the brightest cluster galaxy in the center, and then we have other structures around. But there will also be stars which are not bound to any of these individual structures, what we call cluster light. And these are stars that get liberated during the numerous interactions of galaxies and then live in the cluster. And they also tell us something about the assembly conditions and are basically a time capsule for previous processes in the cluster. Of course, in the simulation, this is really, really easy to understand and to characterize, but observationally, the picture is much more complex. This is a deep image from the Burrow-Schmidt deep survey in the picture, and you can see that there are a lot of diffuse structures going on. So from an observational standpoint, the definition of the intracluster light and intragroup light is a little bit less clear. Some people use apertures, some people use different photometric profiles, but I think we can all agree on that it's diffuse starlight that fills the space between galaxies and clusters and groups. Because tied to debris, if we actually get mathematics, we expect the intracluster light stars to be on different orbits than the halo stars because they are bound to a different potential. But this is very tricky. But this may help us to answer the question, where does the halo actually stop and where does the intragroup light start? Because this is very hard to do from imaging just alone, and whether the same stars actually make up the halo and the IGL, whether we have the same progenitor galaxies in terms of ages, metallicities, masses, etc. However, this is very, very tricky because the closest galaxy group is already not so close anymore, at least if you come like me from the Milky Way halo. And they are too distant. In fact, use individual red giant branch stars as spectroscopic traces. We just don't see any absorption anymore. And as you could have appreciated, I mean, I think this picture goes down to surface brightness levels maybe of 28 or maybe even into the 30s. It is really, really faint. However, the halos and the surrounding cluster light, they are extended. They're still big on the sky, so we can't just plaster my favorite IFU and then say, okay, we put a muse pointing and we kinematics, we integrate long. For example, to map just the halos, a little bit of the environment of one of the big type galaxies in Virgo, we would need about 100 pointings, and nobody will give us time for this. So we use discrete tracers. There are different discrete tracers. The old discrete stellar tracer that we can observe and measure velocities out to, let's say, 100 megaparsec, are planetary nebulae, which are asymptotic giant branch stars surrounded by an expanding ionized gas shell. And stars like our own sun, so low to medium stellar, as a white dwarf. What is very nice about planetary nebulae is that we have a very strong O3 emission at 5007 angstrom and basically no stellar continuum anymore because the star is dead, or whatever remaining radiation there is still shielded by this gas cloud. And so we can use this strong line in combination with the absence of a continuum, both for the identification of planetary nebulae and also for the measurement of radial velocities. There are different techniques to do so. The most classical oldest one is the so-called on-off technique. So we take an image through an on-band filter, in this case, of course, O3, because it's the strongest line. And you see that there are a lot of objects in this image, but only some of them are circle, because not everything that emits in this filter bandpass is going to be a planetary nebula. So we compared with a broadband V filter, and everything that doesn't show up in the V band with some color cuts, we classify as a planetary nebula candidate. But of course, now we've only found the candidates. We would have to do a follow-up multi-object spectroscopy, for example, with fiber spectrographs such as flames, which have a large field of view and a high multiplexing capability. Also, this, of course, is only a cutout from the wide field survey. The whole field of view is 0.5 degree by 0.5 degree in this case. But if I would show the whole thing, we wouldn't see the individual planetary nebulae anymore. So traditionally, this was a two-step process. But there's also an instrument called the PNS that some people are familiar with, which uses something called counter-dispersed imaging, or the technique is also known as slitless spectroscopy. The PNS used to live in the William Herschel telescope. I think we can now finally say that it's been retired because WEAVE has come online. And I think we've also done all the science with it in the Northern Hemisphere that we could. And with this observing technique, we could simultaneously detect planetary nebulae and measure their velocity because we were taking two images at the same time. The instrument has two arms, as you can see here. And then we get two images on two CCDs. If we combine the images and measure the distance between the emission of the two planetary nebulae images, we directly get the velocity. So this really took the field forward because it's really time-saving, it's very efficient, and it was a very stable instrument. What is not so efficient is dealing with counter-dispersed data in terms of data reduction. But with these instruments, so either on off-band imaging and follow-up multi-object spectroscopy, or with the PNS, we get our extragalactic PN populations. And from the photometry alone, just from the narrowband survey, we can already make inferences. Of course, when we have the kinematics, we can do all we want. We can measure radial profiles, we can construct mixture models. And for more nearby galaxies, such as, for example, Andromeda, we can also measure PN abundances, but this gets really, really tricky when we come to the distances that I'm going to talk about. Basically, we just see O3, and if we're lucky, also H alpha, but no other emission lines that we would need to derive abundances. The PN luminosity function is a little bit like Pandora's box. In principle, it's a secondary distance indicator because what you see here plotted is the luminosity function, so counting planetary nebulae in magnitude bins. And And this is already the absolute magnitude, and you can see M31, Cen-A, M33, and the small Magellanic Cloud, they all don't seem to have planetary nebulae brighter than these -4 magnitudes. And in principle, we can use this as a distance indicator. In practice, I would say there are a lot of systematics currently that we don't quite understand how this, whether there is a metallicity dependence. So I would be cautiously optimistic to use PNE to solve the Hubble tension, but some people are trying to do it, and I think for this also some work that I'm going to discuss later is really important, because maybe we can use it in distance ranges to connect kind of the Cepheid scale with the supernova scale. The second important PN characteristic is the alpha parameter, which is basically how many planetary nebulae we have per unit light. The observer's view of this is very simple. We measure how much light we have, we count the planetary nebulae, and then we can make plots like this, where the alpha parameter basically tells us how we can go from the surface brightness axis to the number of PN axis. The theoretician's view is a little bit more cumbersome because the alpha parameter, so how many planetary nebulae we see today, is related to the PN visibility lifetime. And this, in fact, is then related to the specific evolutionary speed of the stellar population. But again, these are only models, and it's not really so well understood yet how alpha correlates with age metallicity of the underlying stellar population. You may have heard of the Extended Early Type Galaxy survey, and some significant NASA's involvement as well. It was led by Magda Baldi, and the first survey paper came out in 2018, led by Claudia Prusoni. The goal of the EPNS survey was to really probe the transition from the central regions to galaxy halos, from the in situ first phase to the second phase of the two-phase formation scenario. What you can see here is a velocity field of NGC 3379, M105, and just by Sauron. So we are really probing very, very different scales, reaching out to 13 effective radii for some of the most extended of those 33 galaxies. One of the main findings of the survey was that the halos of early type galaxies have really more diverse kinematic properties than their central regions would allude to. You may be aware of the slow rotator, fast rotator dichotomy that was proposed many, many years ago by Amselem. But now if we compare the central kinematics here on the y-axis, so V over sigma, versus that in the halo, you can see that it's not that easy. So some of the slow rotators actually start to rotate fast. Some of the fast rotators are slowing down. Some of the fast rotators keep rotating fast. And quite a large number of the fast rotators also have some kinematics that are consistent with triaxiality. So not so easy symmetry profiles either. Claudia used this diagram and then introduced a so-called kinematic transition radius, where we move from this in situ to the ex situ component. What you see here is the transition radius normalized by the half-light radius of the galaxy versus stellar mass, and you can see that at least the global trend of what she measured based on the EPNS galaxies agrees very well with the kinematic transition that was identified also in numerical simulations of galaxies by Andy Cooper. Now, in my work, I'm focusing not on the transition from the in situ to the halo component, but really from the halo component to the surrounding intragroup and intracluster lights. So I picked 2 galaxies that already had PNS data and basically acquired more data even further out. And these are M49 and M105. They live in very different environments, but they are both still kind of nearby. M49 is in the middle of the Virgo cluster, and M105 is in a low mass nearby group. So I don't think the Virgo cluster needs a lot of introduction. It's the nearest cluster to the local group. It's not fully virialized yet. We still have 3 subclusters that are probably going to merge into a superstructure in the next, I don't know how many years. M49 is actually the brightest galaxy in the structure, but it's not what we call the brightest cluster galaxy. This is actually M87 at the center of the Virgo subcluster A. M49 has a very extended halo, a very smooth halo, actually. And what is interesting about M49 is that it has a very blue halo. And this is interesting. Red in the center to a more bluer outer halo, but not reaching colors of B-V lower than 0.6. So the question is, what are the progenitors that have built this envelope? And if we look at simple stellar populations and what kind of ages and metallicities combinations would lead in the B-V color space, of course, we could have a very blue outer halo because we have young stars. But young stars would mean recent merger. Do we see a recent merger? No. How about very metal poor stars? Fair enough. But then if we would place our galaxies, our progenitors on the mass metallicity relation, we would need very, very many few galaxies with merger mass ratios of about 1 to 1,000. And this, unfortunately, is not the dominant channel of halo growth predicted in cosmological simulations to this date. So we really need to assess the dynamics of the halo. Before we do this, I want to briefly talk about what we can learn just by counting PNE from our narrowband survey alone. What you can see here is a comparison of the PN number density profile with that of the stars. I think this is the profile from Capaccioli. And you can see that in the inner halo, they agree really remarkably well, as we expect from planetary nebulae, because they are stars, they should trace the stellar light. But then in the outer halo, we have more planetary nebulae than we expect per unit stellar light. And we can model this by having a two-component surface brightness profile, because you can see also the stellar light profile starts to deviate from the R to the 1/4. And give the second profile, this flat profile here, that was just our toy model for the surrounding intragroup light, a higher alpha parameter. And we find a 3 times higher alpha parameter in this blue outer halo. And interestingly, this is consistent with what Alessia Longobardi saw in the outskirts of M87, where there are also more planetary nebulae than you would expect by just looking at the stellar surface brightness. And because we have this color information, we can also look at alpha in a kind of continuous way, and we see that alpha increases from a low value consistent with that of early type galaxies collected by Busoni, and then in the outer halo, we have values that look more like what we would see in local group dwarf galaxies, such as Sextans A, really, really diffuse objects. And this may also give us hints about the progenitors. There are some issues with this diagram that I will address later, but it can give us just an idea about formation channels. And hand in hand with this variation of the alpha parameter also goes a variation in the PNLF slope. I think this is very intuitive because in order to have more planetary nebulae in the outer halo has a much steeper slope than that in the inner halo. So because it rises more quickly, we also see more planetary nebulae. And this is interesting because people previously thought that this slope is always constant at 0.307, but you can see it's really not a very good fit to the data. Now let's have a look at the kinematics. These are smooth velocity and velocity dispersion fields. So far, we color code our smooth fields at the points where we took the measurements. Of course, a single point cannot have a velocity dispersion. And when I created this field now a long time ago, my supervisor came back to me during the PhD and was like, this doesn't look like a giant early type galaxy should move. This is messy. Probably you did something wrong. Not really, but it turns out that we have more substructures in the halo that we need to take account of. And back in the day, we cross-correlated the velocities with the very accurate photometry from SuprimeChem that we had, and we looked at the folded velocity versus magnitude, and what we saw is that we have really a peak along the southern major axis, but also a little bit on the north of bright planetary nebulae that co-rotate, so that really move different than the rest of the halo. And it turns out that if we now divide the sample into bright and faint and we redo this plot, you can see that the faint sample really looks like what we would expect from a massive early type galaxy. We have some moderate rotation about the minor kinematic axis. But what we see in the bright component is that we actually have a dwarf galaxy falling in, VCC 1249. And because it has a different velocity relative to M49, we see this hotspot here on the velocity dispersion map. Yeah, this is how the accretion looks. This could merit a talk by itself, and I currently have a master student working on this interaction because we have been just finished observing news data of this dwarf here. And what's interesting, we have planetary nebulae that are probably stripped. We have gas, H1 gas from radio that is stripped. And we also have H2 regions, so star-forming regions that were triggered in this interaction. So this may be a very nice environment for a galaxy dynamics experiment on dwarf galaxies, because depending on the galaxy's potential shape, whether it's cusped or chord, it may evolve differently as it falls into the halo of this very, very massive galaxy. But let's talk about the faint PN population, which is not contact the line of sight velocity distribution, where we also expect signatures of the intragroup light. So if we put everything on a sigma versus radius plot, you can see the red points for the faint component. We see basically a flat line of sight velocity distribution and dispersion, and then we see a strong increase in the outer at large radii. And this is a telltale sign, this increase in sigma, that we are moving into the intragroup light. This is also seen in simulations that, and also based on absorption line kinematics, just long slit data. And what I'm showing here for comparison is now the velocity dispersion of a sample of dwarf galaxies orbiting at different radii from M49, and you can see that this increase then continues in the dwarf galaxy sample. And so you can see that we're really tracing the same bulk motion with the planetary nebulae at very large radii from M49, as well as with these dwarf galaxies. This is how the line of sight velocity distribution looks like, and we can do a simple two Gaussian decomposition, and you can see that the line of sight, that the profile for the IGL PNE has a much larger dispersion, twice as much nearly as that of the halo. And then we can just, draw some colors basically for all of the planetary nebulae in our sample, and you can see that the IGL is not the donut. This is just one representation, but it's not like, we have the halo and then we have the IGL, but we have objects kinematically consistent with being on IGL orbits also on top of the galaxy. And this is how the IGL fraction looks like as a function of radius. So it's not like galaxy, 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 IGL, IGL, but it's really at all radii, I think, a superposition of the two. So now putting everything together, that we have the smooth photometry, high alpha, featureless velocity field, we can make some inferences about the properties of the IGL around M49. And we think it's probably very metal poor because the smooth halo plus the kinematics that we measure lead to a dynamical age older than the orbital precession time of about 5 gigayears. So a lot of these isochrones we looked at before just are now out of question. So we think we have a really low mass system of progenitors. So when I did this about 5 years ago, simulations were not good enough to really resolve dwarf galaxies of these masses. I think we're slowly getting there, that we have a big effect that we didn't see this channel prominent in the simulations, but more a resolution effect. But I think this is something for the simulators to figure out. But M49 has been a really interesting system to study, both for the IGL, then this surprise. I mean, we knew that the dwarf galaxy was there, but that we could tag planetary nebulae with this interaction. And also I want to stress the high alpha correlating with the blue color. Now let's move a little bit closer to home, to M105 and the Leo 1 group. It's a very different environment to Virgo. Okay, this is a zoom in just on the main players of this talk, but the Leo 1 group has maybe a few hundreds of galaxies, only a few hundreds if we count all of the dwarf galaxies, but there are really only like 5, 6 very massive galaxies. So yeah, very, very, very different from Virgo. That would be somewhere here. The Leo 1 group is the closest galaxy group that contains all galaxy types, and it's surrounded by a ring of H1 gas, whose origin still debated whether which galaxies had to interact and which galaxy lost its gas to make this huge ring. And it has a much, much lower intragroup light fraction of just a few percent. And I think also, Rosella, your measurement agrees with that, right? Yeah, but very different from Virgo, where it's, 30, 40. So also here we've extended, this was the PNS field that I've shown you in the beginning, and we've built a mosaic around with former fields that I observed during my PhD, and then this was part of Ariana Cortesi's work on S0 galaxies with the PNS. And what is really nice, because the galaxy is so close, is that we have photometry from HST, so we can make inferences about the ages and metallicities from resolved stellar populations. So this is how the metallicity distribution functions look like in these two fields. So we have an inner halo field here and an outer halo field there. Inner halo, basically mostly metal-rich stars, 0 DEX, and then as we go to this outer field, we have this excess of metal-poor stars, and here's a comparison. You can also look at the spatial distribution. So the metal-rich stars basically nearly follow the R to the 1/4 light profile, and the metal-poor stars are, the really, really metal-poor stars follow an exponential surface brightness profile. We can put the starlight on top, and we can put the planetary nebulae on top, and surprise, surprise, again, we see an excess of planetary nebulae compared to what we would expect just from the light. But now we can inform the second component of this model from the number density distribution of the very metal-poor stars. And we again find a very high alpha in the exponential envelope. And for the first time now, we can directly correlate that we see a high alpha parameter, higher than in the inner halo, with a metallicity measurement and not only with the color, because we always suspected that it may be metallicity that is driving this, but we didn't know. Of course, this is just one galaxy, but I think it's a good start. Again, also kind of logically following is that we observe a steeper slope of the luminosity function in the outer halo compared to the inner halo, and here I didn't even bother to put the standard slope on anymore because it really does not fit anymore. What is really exciting about M105 is that based on just the central field, is that there was quite a heated debate 20 years ago about its kinematics, about whether it may be dark matter free, or whether it's just a viewing effect depending on the mass shape anisotropy degeneracy. But now we have more data, so let's see. To address this problem, I first need to introduce the imposter, which is NGC 3384, which is unfortunately also a group member and rotating such that we really have the same velocity range for both galaxies. So I did again a Gaussian mixture model, this time informed by the photometry, and basically for each planetary nebula in the sample, I could get a probability to either belong to the bulge or the disk of NGC 3384, or to the inner halo or the exponential envelope of M105. And now we just forget all the planetary nebulae are associated with other galaxy and just focus on M105 kinematics, because now we have a clean sample, and the signatures that we see at large are really signatures of M105. So we can look at rotation. What you see here in the center is the transition that already Claudia Personi identified in her paper, just based on the central from the rotating core to the halo, where we really have basically no rotation. And then if we go into the outer halo, we see high rotation, and we also see a change in the kinematic major axis. So basically, the kinematics flip from being aligned with the galaxy's major axis to the minor axis at large radii. We can quantify this rotation support by the so-called lambda parameter that was introduced by Amselem. Basically, if we have a lambda parameter over 0.1, we have a rotation support, and if it's below, it's dispersion supported, and we can use this diagram to components, so rotating core, halo, and then the exponential envelope. If you want to look at more lambda profiles of 33 other galaxies, I want to point you to Claudia's work, which was really a Herculean effort on measuring angular momentum in early type galaxies, which is really not trivial. But to look at the transition to the intragroup light and the exponential envelope, we should also look at sigma. So this is the line of sight velocity dispersion profile just based on the central field, and the one that is consistent basically with just Keplerian motion and no dark matter. But now if we put all the new data points on top, it's very clear that, you know, this increase of velocity we cannot do just with Keplerian dynamics. We need some additional mass. And again, we can also, now that we have this two-component model, we can have planetary nebulae associated with the inner halo. And then in the exponential envelope, we have a much higher velocity dispersion. And if you do a simple GEANS model, this is actually what you also would expect because we have a flatter light distribution. And again, what is interesting is that if we look at the motions of individual galaxies in the LEO group, now take this measurement with a grain of salt, because some galaxies with kinematics don't have very concise distances. We again see this kinematics consistent with that of the larger scale motions of the group. And what I want to highlight is this is a transition that was identified by Rossella and Enrica based on VST data. And also this innermost transition that we identified completely independently. We did not talk to each other before the papers were out on the kinematic agrees very well with a break in the very deep VST photometry on this galaxy. So it's really nice to have two independent measures of it. We can revisit this picture that Lee and Young actually painted based on their HSP data on the assembly of a system such as M105. So the inner matter-rich halo probably formed either in situ or maybe whether through a very major merger of a few systems, few massive systems. And then what they call the blue halo mode, maybe looking at the kinetics more, the blue IGL mode, is this dissipationless merger accretions of very mass subsystems. So M105 is our most extended sample of PNE in a group-dominant galaxy. And it's been really a blessing to find this additional metallicity data to link the PN-rich halo and the metal-poor stellar population. We are working on a dynamical model of the system to finally put an end to the debate of whether there's dark matter or not. Yeah, I think this has opened the doors for what we are doing now. Because I hope I could convince you in the last half an hour that we can measure large-scale kinematics easily with planetary nebulae. We can look at kinematic transitions. We can use them as a distance indicator, but the galaxies we are studying anyways have very well-determined distances already. And we can look at the stellar light distribution. But what we cannot do currently is to measure stellar population properties, because the other lines of the PNE that you would need to measure abundances are not available to us at these distances. But we see these first correlations of alpha and the PNLF slope with metallicity measurements. However, if you look at where we measure planetary nebulae and where you or people would measure HSM metallicities from integrated light, from NEWS data, from Sauron data, this is how a slitless spectroscopic image looks like. The galaxy is so bright that we basically just do not detect planetary nebulae on top. So basically, we measure planetary nebulae here. We measure HSM metallicities there. So also the plot from Bosoni that I showed you before, where I showed alpha as a function of color, it's not really a co-spatial measurement at all. well, the color maybe, but there's also some with metallicities and ages, which were definitely not taken co-spatially. And this is where integral field spectrographs come to the rescue. So my favorite one, of course, is MUSE. And we can use integral field spectrographs to disentangle now pixel by pixel the nebula and stellar contribution to the spectra. And we use a technique called DELF for diffuse emission line filtering, because we can really build narrowband images as small as the spatial resolution of MUSE, which really helps us to boost the signal of the individual planetary nebulae, because they have a very, very narrow full-width half maximum. And if we do so, this is an animation that my former student Anna Ennis has made during her PhD. We can really detect planetary nebulae. This is just 1 square arc minute, typical MUSE field of view, on top of the galaxy. And because we have the MUSE groups, we can also measure now ages and metallicities. So hopefully we are now going to build a statistical sample of alpha. Maybe PNLF is a little bit tricky because the field is small, we don't have so many planetary nebulae, but alpha, ages, and metallicities measured all in one space from one data cube. And we've already done this exercise based on commissioning data that was taken about 10 years ago in the center of M105. So this is very similar to a plot that I've shown before, and you can see that we have this gap in the middle where we don't find planetary nebulae, neither with the PNS nor with Subaru. Slowly starting to fill the gap. There's still a little blind spot here, but we are getting there. And now we can actually put everything again on an alpha metallicity diagram. We have metallicity from the pencil beam HST survey here. So this may not be representative to the entire halo, but this point is really taken co-spatially, whereas these points maybe not so much. So I think this is really an exciting avenue, and stay tuned for Anna's paper that hopefully should come out early next year on mapping all the EPNS galaxies that are also accessible from the Southern Hemisphere with MUSE. And lastly, I've now been talking for 35 minutes about IGL, but this week at ENAF, I've been looking at very faint and diffuse, ultra-diffuse galaxies. I think it's also interesting from the IGL perspective, because ultra-diffuse galaxies, ultra-faint galaxies, are viable progenitors of the metal poor stars in the IGL and may get reprocessed in the IGL, because of course they're fairly easy to destroy. But you may be aware of Enrica's MUSE large program, LUIS, which is targeting dozens of ultra-diffuse dwarfs, ultra-diffuse galaxies in the Hydra cluster. This is just one of them. This is UDG 11 that was published recently. And what I've done in the past year is to really go into the belly of the MUSE data reduction pipeline and optimize it for these diffuse objects. Because you can imagine sky subtraction for systems like this is very, very difficult, because you don't know whether a pixel here is still galaxy or whether it's already sky. And I think we've done quite a good job now. I think we are also confident that we are not introducing more artifacts than we are removing. And this week we've implemented my data reduction flow that was running on a moderate server in Finland here on the machines here, so that Goran can reduce the remaining 30 or so UDGs with the improved pipeline. And then we've also been looking at a very, very interesting system, I think most challenging system from the data reduction point of view, which is UDG 32, which is in the vicinity of this galaxy with this very, very extended stripped, RAM pressure stripped gas tails. And we thought when we prepared the observations that, yeah, the gas tail is here. There was very deep VST observations. But now if we look at the MUSE data, and we can, of course, create a pseudo-narrowband image, which is great. It's interesting, but it makes it very, very hard to deal with the data, because in the first reductions, even with my improved data reduction routines, the pipeline thought that the emission lines from the gas, because they're not super broad, were skylines. So out of the sudden, we found fake absorption everywhere in the cube. But this is now sorted. We can start. We are doing science now in this, and we are trying to confirm that indeed the UDG and the filament are at the same redshift. If they are at the same redshift, it means that basically the emission lines of the filament cancel out the absorption from the underlying UDG. So it's very challenging to measure, but hopefully the next time that I'm coming to Naples, I'm going to talk 40 minutes on this interaction, and hopefully we'll know more very soon. I think I'll leave you with my summary. Planetary nebulae are great traces of the diffuse IGL, and we've used them to observe kinematic transitions both from the in situ component to the halo, but also from the halo to the intracluster light. And I think the combination of planetary nebulae with metallicity measurements, either from HST imaging or with MUSE in the centers of galaxies, is really the way forward to elevate planetary nebulae as a stellar population tracer and not only as a discrete tracer. And yeah, that's it.